Hi, my name is Danilo from University of São Paulo, Brazil, and I'm going to present this work. In introductory course of technology, students with difficulty in programming subjects have led to high dropout rates due to difficulty to understand algorithms, programming language, and the concept of paradigms. Furthermore, teachers encounter challenges to support students individually, when adequate feedback is essential to the learning process. Several works have been proposed to support learning of object-oriented concepts. Although the object-oriented concepts are taught in different ways, it becomes hard to identify the students' difficulties concerning code quality, good programming practice. Usually, the evaluation is based on the results of exercise and projects, allowing to teacher to effectively analyze the understanding and compliance of the students. The main problem is the time-consuming task of analyzing each project, considering multiple source code and number of projects. Several studies suggest that teaching software quality should begin as early as possible. Good practice could help students to think more critically while learning programming concepts. In this paper, we present the teacher-made tool to support source code analysis to identify the lack of good programming practice and students' difficulties. This tool uses a source code analysis framework to static code inspection to identify the violations of students' source code and difficulties. TeacherMate is a web-based application to support teachers to identify the students' difficulties in learning good programming practices through violations detections on source codes. This tool uses quality reports provided by SonarQube Scanner, which is responsible to perform source code analysis by verifying the compliance of source code with a set of rules or quality profiles. Thus, SonarQube identifies which part of the code had a bad implementation. TM2 has two main goals: show the students difficult in learning good programming practice to a teacher, and also to present to the teacher whether the difficulties increased or decreased over time. This diagram shows the integration between the TeacherMate tool and the SonarQube API, and the steps to provide the different visualizations. The TM server requests the projects from TM's storage. For each project, the TM scanner calls Sonar Scanner. When all projects are analyzed by SonarQube Scanner, TeacherMate server requests the quality report from all the projects process and send them to the TeacherMate web, so the TM web displays the data properly. The TM tool provides a communication channel between students and the teachers, in which students submit their paper through the tool, making it easier to the teacher to get the student's project. After the projects are submitted, the visualization stage shows reports so the teacher can analyze violations of a particular class. We performed some case studies, and in this whole case study, we select the object-oriented programming course from the computer science degree of the Unesp, Faculty of Science and Technology. We collected the projects applied to classes from 2013 and to 2018 as a dataset. In all classes, the project proposals and the teacher were the same. Two projects were required. The first required the development of a sales system, and the second project we required the development of a library system. The second project had a greater complexity when compared to the first one. Therefore, students had already advanced in learning new object-oriented program concepts. For the case study, 3 cases were considered for selection. First, the projects in which the same student or pair or threes performed the project 1 and 3 together. So it's possible to evaluate the performance between the first and the second project. The second condition, when the projects were developed in 2 or 3 for the second project, and there was a breakup of the group from the first project to the second project, we copied the second project to the individual who get a part of the initial group. Only projects developed 31 is the only project that developed in Java language was considered due to the SonarQube limitation for this TM2. From the selected project, we extracted the violations that occurs in particular class and violations that occur in all classes. We discarded all violations that are false positives generated by IDE, such as an example, NetBeans GUI. Through the dataset, a case study was developed with the following hypotheses. The first one, is there a pattern on the violations found in the first project? Is there a pattern on the violation found in the second project? Is there a correlation between increasing the number of lines of code and increasing the number of violations? Is there an increase in the number of the violations found from the project 1 to the project 2? Is there a decrease in the number of blocker severity violations in project 2 compared to the project 1? We are going to analyze all these hypotheses. To select the set of common violations committed by students, the average probability metric was proposed and used. For example, suppose that X is one of the violations belonging to the bug class. For instance, resource should be closed, and along all the selected projects, the violation X occurs 100 times, as well as the total of violations from bug class is equals to 200. So the probability is 50%, representing that 50% of all bug violations represent the X violation. In my example, it could be resource should be closed. The 5 most common violations found in project 2, here is a table to summarize or analysis. The 5 most common violations found in project 1 were presented in this table. And there's a dominant specific violation. Almost 70% of all bugs found in all first projects correspond to resources should be closed. It is a violation of not properly closing the resource utilized in use. This happens because students have not formally learned about try-catch structures, which is not a part of the course discipline. The second position is in the table is class variables fields violations should not be public, which with almost 50%. This vulnerability occurs when class attributes are used as public, disagreeing with the encapsulation principle, probably because the students are not getting used to this concept in the first project yet. Third position is a violation publicly static fields should be constant, because the studs are not used also to the database, so some static variables were used to simulate a database connection. The fourth position is a null pointer violation, because even though the project is simple, there are few declaration of variables and the students are not used to checking and the the pointers. The throwable print stack should not be called violation, which occupies the 5th position in the table. It occurs because, according to the center cube, students must use logger instead of print stack days. According to the first hypothesis regarding to the first project, we found out that there is a dominant set of violations, referring to the classes from 2013 and 2018. And according to the questions, there is a group of violations that occurs predominantly in most of the projects. Compared to the violations of the project 1, it's clear that the second and third position of the table does not change when we analyze here the violations to project 2. Class variables fields and public static fields are the same position, but the first one is replaced from resource should be closed to no pointer should not be differentiated, possibly indicate that students are more concerned about closing files in the second project when compared to the first one, but failing to check if the variable is null. There is an increase in the number of variables declaration and giving students less practice and experience. There's a little concern to avoid null pointer exceptions. They are not used to verify if a variable is null after using this variable. Class variable fields should not be publicly corresponding to the 5th% of all vulnerabilities, indicating students are not yet applying the encapsulation concept. There is also a significant decrease in the resource should be closed, showing that a portion of students has learned to deal with it. According to the second hypothesis, we figure out that is also a pattern of the violations found in the second project. Here we are going to show analyzing a correlation. We analyzed and we perceived that there is a high correlation between the quantity of lines of code log and the number of violations. This correlation is almost 93% of positive correlation, showing that the greater the quantity of the lines of code, the greater is the number of violations. In addition, on average, project 2 presents a higher line of code number of lines of codes when compared to project 1. Other hypothesis states that there are fewer blocker security violations in the second project compared to the first project, even if the second project has a larger the line of code number. This remap is presented to show the number of lines of code as the size of the rectangles, and the color follows that color scale to show the number of blockers violations. Although the second project has a larger area, a larger number of line of code, its color is lighter, indicating fewer blockers. So the second project is bigger, but the number of blockers violations is fewer. At last, we compared 5 most common violations from project 1 to the most common violations from project 2. This bar chart shows side by side the number of violations in project 1 and project 2, and alongside a legend for identifying these 5 violations, main violations. Notice that both research should be closed and class variables should not have public accessibility decreased, even though the students still make such mistakes. The public static fields should be constant. Violation increased because project 2 has more reading and writing files than project 1. What's notable is that the larger growth of the number of null pointers violations, which occurred due to the increased complexity and variables declaration in project 2. Finally, the decreasing of throwable print text trace should not be called violation, indicates that students have begun to adopt the correct array of using logger in the project or use the suggestion of the IDA, such as the suggestions of NetBeans. Using TeacherMate 2 in the beginning of the OP classes in 2019, the teacher made changes and reinforced some concepts between Project 1 and 2. This table shows an improvement in the year in this year when the teacher used TeacherMate 2, considered all violations classes, bug vulnerability, and code smells. There is a smaller number of violations when compared to all previous classes, showing that the intervention of the teacher after using TeacherMate 2 was beneficial. Here also, considering the total number of metric of violations of a given class per killoc, 1000 lines of code, killoc, we calculated an index as follows. The number of violations per killoc computed at Project 2 is subtracted from the number of violations per killoc computed at Project 1. We subtract considering each class. For instance, bugs from Project 1 are subtracted from bugs for Project 1. 2 from Project 2 are subtracted from bugs for Project 1. Thus, positive index represents a decrease in the number of violation class in the second project for every killoc. It's notable that the years 2018 and 2019 are the only ones with all the positive index, and that only 2019 has the second highest index of bugs and vulnerabilities, presenting a better performance compared to other years. Although it does not have the highest index, it has great and positive indexes, indicating that after the intervention of TeacherMate 2, the student's code quality comprehension has improved. We consider that the teacher intervention had a positive reflection comparing the issues with the previous classes, demonstrating that the two provided insights to the teacher. This paper represented these two to support analysis of violations, code quality, code smells, and also to identify students' difficulties. In the case study, we observed that there are a common group of violations in both projects, and a correlation between lines of code and the increasing of the vulnerabilities. And also, regarding the code quality, the tool is good to identify them and showing that the use of the TM2 is beneficial. The changes done by the teacher were his responsibility, but this tool is able to provide new insights on what change need to be done in a course, and also we observed that the TeacherMate 2 contribute to decrease the number of violations from Project 1 to Project 2. For our work, we'd like to intend to provide a way to compare performance of each student in a specific work and integrating TeacherMate with other tools to directly support the students. Thus, we could create an environment to support the teaching learning process in information technology course, improving the learning of code quality in the education environment. They are my contact. I'm available to respond, to send you a feedback if you contact me. Thank you so much.